I don't know if I hear anything, but we'll see. Yeah, there's sound now. I heard something. Yeah.
The monitor of the Zoom call, I can't seem to be.
Oh, it's okay. It's fine.
Sorry.
Okay.
Hello all, I hope you can hear me.
Sound. So the mic is now the meeting out and the speaker should.
Ça marche bien, ça tue aussi les acteurs. Déjà, on a
Because when I start the presentation, I won't be able to change anything.
Mais on se connaît très bien de présenter.
D'ailleurs, on va se battre souvent parce que je vais venir, j'ai découvert que j'ai un bureau.
T'as un bureau?
Ah, il fait pas des... Oui, non, mais bon, avec beaucoup de monde, moi. Mais bon, j'ai une clé, là. Je me suis connectée avec Voilà, c'est le début de l'intégration. Voilà.
C'est la grande partie.
Voilà.
Le Yeti, j'arrive pas à faire fonctionner. Le Yeti, j'arrive pas à le faire fonctionner. Il apparaît pas dans OBS, ça m'énerve un peu. C'est la première fois que ça arrive. Après, c'est pas grave, on a le son. J'ai déjà été tout comprendre. Il apparaît dans le lieu, il y a OBS. Ouais, non, je peux le faire, j'ai déjà fait plusieurs fois. Mais il est pas mal. Le micro du hibou, c'est pas le micro du hibou, c'est le micro du zoom. J'utilise le micro du zoom, mais ça va. Ok. En gros, c'est vu que le zoom, comme ça, j'entendrai directement sur la micro.
C'est quel que j'ai le hibou sera bon, ça.
Ayush,
Pas dans ma vie.
tu veux que je cherche un. Non, c'est bon.
Mais on est dans le même labo, ça me permet de dire. Ok.
Là, on accorde, là, il est.
I guess that you got to speak in English.
I understand enough French to make
Yeah, but-
the things, but let's
Maybe
do
it should be more convenient.
one of the jury members who's joined from India only speaks English, so.
Okay, in this case,
Who's on the,
I will keep.
you are on the
English
call,
as the
right?
main
Could you
language.
open your, so that Satya can see the jury.
Which one?
Yeah.
Ayush?
Thanks.
Okay, so it's our pleasure to be there today for your PhD defense with this amazing jury where we have David Bromberg, who is professor at University of Rennes, who is professor at University of Neuchâtel. Then we have Satya Peri, who is professor at IIT Hyderabad, remotely. Stefania Dumbrava, who is associate professor, sorry, at ENSIE. We have Julien Sopena, who is there, who is associate professor at Sorbonne University. We have Marc Shapiro, who is a senior researcher and emeritus from INRIA. we have Swan Dubois, who is associate professor at Sorbonne University, and myself, I'm a senior researcher at INRI.
And Isaac, who's not here,
Is not,
is on sick leave.
yes.
Before we start, could we make sure that Satya can see and hear us? Are you okay, Satya?
It was, now I can hear.
Do you
Can you
see?
hear me?
Yes, we can.
Earlier it was not audible. Now I can hear you, and the screen is, I can see you, the screen that you're sharing, Ayush.
Okay.
On the screen, I mean, not the screen behind you, the
You
one
don't,
from your computer.
okay, you don't see the video?
Which video you're referring to?
Of the meeting room? Do you see the meeting room and?
Yeah, I see. Yeah, I see
Okay.
the people, everyone here. Yes. Okay.
Okay.
And I can see the slides that you're sharing through the Zoom, not the screen behind you. Seeing the screen behind you is more difficult.
All right. Okay. So then I'll start. Good morning, everyone. Welcome to my PhD defense. The domain that I work in is called multi-granularity locking for hierarchical data. Before I go into the technical jargon that you see in the title, I want to take a moment to first thank the jury members for taking time to read my manuscript and also be present in the jury here. Second, the members of my CST who helped align and narrow down the topic of my research over the last 3 years, and most of all, my supervisors, without whom any of this work would not have been possible. Now let's dive into the technical stuff. So the topic that I work on is called multi-granularity locking for hierarchical structures, and I want to introduce hierarchical structures first. They have a few properties. They are directed graphs which have a designated root. So for example, in the slide, we have A as the root of the hierarchy. Typically, data is stored in the vertices in the form of name. This data is represented using the edges. These kinds of data structures are used in a variety of domains. One of the most well-known and ubiquitous is file systems, where we have a root level directory that contains some subdirectories which may or may not have files in there. Management, where we manage control or user data from one process to another. And the third, more recent one is JSON data stores, which are nested objects that contain key value pairs. Now, because I'm focusing on data consistency and synchronization, I will focus on JSON data stores as a motivating example and show how JSON data basically encodes a hierarchy. So on the right, we have an object that contains a set of nested objects that each contain an ID and a list of children, which in themselves might be strings that refer to other objects or defined objects themselves. So the root object is A, which is also the root of the hierarchy. It contains two objects, B and C, which are the two children of A. Now B itself contains several objects, which I've abstracted here for the sake of brevity. C contains an interesting object, which is G. Now it's interesting because it contains a reference H that was already defined as a child of F. And we have that as a reference within the object G to the original definition of H. Similarly, we have a directed reference from I in J to the definition of I in G. And in this way, we see that a JSON object is basically a hierarchy. Now, when we have data objects, we can perform operations on them. And a typical well-known acronym for operations that we can perform on data is CRUD, which is create, read, update, and delete. CRUD operations for hierarchies can be categorized into two broad categories. First is non-structural. And non-structural operations don't change the topology of the hierarchy. So we're not creating any data or deleting any data from the hierarchy. So for example, reading a vertex or reading several of them. The query here is, does A have a grandchild named G? And the execution of this query involves reading the vertex A, navigating some edges based on predicates, and then returning true or false. Structural operations, on the other hand, change the topology of the hierarchy, either by creating data, for example, adding a vertex with the ID k and name k, creating relationships between vertices by adding edges between them, or deleting and adding relationships. So for example, we are deleting the edge BD from this hierarchy. Now, when threads issue these operations concurrently, there is a need for synchronization. In the example that you see in the slide, there's two threads, T1 and T2, both doing some operation on the hierarchy, and they access an overlapping set of vertices. In this case, we have T1 accessing E and F, highlighted in blue, and T2 accessing F and G in order to perform a reachability check between them. So we see that T2 starts a traversal over F. Meanwhile, T1 deletes E. Until now, there's no problem because none of the overlapping data has been modified. T2 traverses H, and concurrently, T1 comes along and deletes F. And at this point, T2 returns true because according to T2, the path between F and H exists. But in reality, vertex F was concurrently deleted, and this leads to an inconsistency. So the problem is, how do we ensure that these overlapping sets of vertices or edges for that matter, that two concurrent threads are accessing don't lead to inconsistent states? And one of the ways is to basically lock the vertices in advance and then ensure that the threads remain isolated. Now, before I go into the locking protocols that achieve this isolation, I would like to first introduce a few terms that I'm going to use repeatedly in the presentation. And the first term that I'm going to introduce is the lock target. Whatever vertex or edge that a thread wants to access is called a lock target. And throughout the presentation, they're always going to be highlighted in pink. Now, based on the lock protocol, for a set of lock targets, we might end up locking one or more different vertices in the hierarchy. And the vertices that we actually lock are called lock guards because they guard a set of vertices. Because a single lock guard can lock several different vertices, the vertices that lock guard guards is called its grain, and the size of this grain is called its granularity. So in the slide, hierarchy that you see on the slide, A is the lock guard that guards vertices that are highlighted in yellow and pink, and that's its grain. And the size of this grain, which contains all of these vertices, is its cardinality, which is 10, and that's its granularity. Now, based on the granularity, we have two extremes. First is fine-grained locking, where the lock targets and the lock guards are the same vertices. So every single vertex has its own unique lock guard. And by acquiring a lock on that lock guard, we lock just one vertex. And on the other extreme, we have coarse-grained locking, where the whole hierarchy is associated to a single lock guard. Now, as is evident, fine-grained locking allows for the maximum amount of concurrency because we lock the smallest possible unit in the hierarchy. But because we are acquiring a lot of locks, this has a high locking cost. Coarse-grained locking, because we guard everything with a mutex, it does not allow any amount of concurrency, but it consequently has a very low locking cost because every thread is synchronized at the same vertex. Now, both of these extremes have their advantages and disadvantages, but the domain that I work in tries to find a balance between the two. And it's called multi-granularity locking because the granularity of the lock depends on the lock request and the topology. There are several examples. One of the oldest ones is intention locks. It was published somewhere around the 1970s, and more recent ones, which are DOM lock, multi-interval DOM lock, and flexigram. Now, within this domain of multi-granularity locking, we have three main challenges. First is the granularity dilemma, which talks about the balance between this coarse-grainedness and fine-grainedness of locks. We know that coarse-grained locks don't allow concurrency, while fine-grained locks are expensive, so we find a balance between the two. Second is, because we are not dealing with just data or vertex-level conflicts, we need, and talking about overlapping grains, we need an efficient way of detecting conflicts between these kinds of lock requests. And third is lock protocols that typically are implemented with some metadata. That metadata should not be so expensive that we negate any performance benefit that we get from doing this multi-granularity locking. Now, with these three challenges in mind, I would like to now introduce some state-of-the-art protocols. And I'd like to start with the oldest one, which is intention locks. So the idea behind intention locks is for a thread to be able to lock a vertex, it has to indicate its intention somewhere higher up in the hierarchy. So in the example that we see on the slide, in order to acquire a lock, an exclusive lock on G, a thread has to first acquire a lock on A and C, which are its ancestors. Now, to achieve this, intention locking has three new lock modes. Intention shared, which indicates that one of the descendants of this vertex is locked in shared mode. Intention exclusive, which indicates that one of its descendants is in exclusive mode, and shared with intention exclusive, which indicates that the current vertex is locked in shared mode, while one of its descendants is locked in exclusive mode. And the protocol basically says, in order to lock a vertex, it is required to lock all of its ancestors in a corresponding intention mode. So if I'm acquiring a lock, exclusive lock on G, then I have to lock all of its ancestors in an intention exclusive mode. Let's see how that works in practice. So a thread wants to lock two vertices in the hierarchy, G and H. They are pinned because they are lock targets. It starts a traversal from the root, acquires an intention exclusive lock on A, goes down to its first child, takes an intention exclusive lock on C, then goes down to G and finds that it has reached one of its intended lock targets. So it acquires an exclusive lock there. Now G is actually locked. Then it goes back to the root and does the same thing for the path to H. And then it locks H in exclusive mode. Now, when I talked about the challenges of multi-granularity locking, I use this term grain. Now, the grain of a lock and intention lock basically contains all of the ancestors of a lock target. And that's highlighted in this blue dotted line. Now, with intention locks, we run into a few problems. First is that we need a significant number of traversals because we have to navigate through all of these paths in the hierarchy to lock the vertices. Second, conflict detection is also expensive because it happens while we are acquiring a lock. And when we do encounter a conflict, we have to release all of the locks that we actually held and then retry at some later point. And third, when this order of locking paths is non-deterministic, then we run into deadlocks. So if a thread comes along and first locks ABD and another thread locks ACG and then wait for each other, we run into deadlocks. Solution to these issues is we first would try to eliminate these traversals by somehow making sure that by using some metadata that basically summarizes this path property. And second, by eliminating the use of multiple locks per lock request. And that's what the next protocol that I'm going to introduce tries to do. It's called dominator-based locking or DOMLOCK. Now, DOMLOCK is based on this subsumption property that says a vertex subsumes all of its descendants. So in this hierarchy, vertex A subsumes every other vertex in the hierarchy because it's an ancestor of all of these vertices. Now, this subsumption property, instead of explicitly traversing paths, is summarized by a labeling scheme in DOMLOCK, which uses a post-order traversal to identify these integer ranges. Let's look at how labeling works for DOMLOCK. So it's a post-order traversal over the graphs, and we give an integer range with the form XX to every leaf vertex and YZ to every inner vertex. So in the hierarchy that we see on the slide, D is the first post-order vertex, so it gets the integer interval 1, 1. Then E gets the interval 2, 2 because it's the second post-order vertex. Now, once both of the children of B have been labeled, we give it the interval 1, 2, which is the smallest possible range that subsumes the range of its children. Similarly, H gets 3, 3, and we label every other vertex. Now, only after both of A's children have been labeled can A be labeled. and it gets the range 1, 4, which basically now subsumes all of these ranges in the hierarchy. Now, in this kind of a labeling, this post-order traversal propagates these integer ranges from the leaves to the root of the hierarchy, which, as we are going to see later, causes some problems. Now let's look at how we actually acquire locks in a hierarchy. Instead of explicitly using these paths, we now use these integer labels. So in this example, the same lock request, a thread trying to lock G and H, instead of traversing these paths, just takes these integer ranges, which is a write lock on this range 3, 4, and 3, 3, which is the G has the range 3, 4, and H has the range 3, 3. And we find the smallest range which is sufficient to lock the set of these ranges, and that's 3, 4 in this example. Now we require just one traversal over the hierarchy to find a vertex with this range. So to do that, a thread starts its search from the root again, goes through different vertices. It encounters C, which has the interval 3, 4, but it might possibly find another vertex with a proper interval somewhere down in the hierarchy. It goes down to J and sees that it has restricted search too much. So it backtracks and acquires a lock on G. And as soon as it acquires a lock on G, any vertex with an overlapping range is considered locked. And that's the grain of this lock request. So a lock on G with the range 3, 4 locks every vertex with a range that lies in this range 3, 4. And that's all of these vertices. And there lies the first problem with DOM lock. With multi-granularity locking, we should ideally lock only descendants of a vertex. But with DOM lock, we are locking its siblings because of these integer ranges. And we call this problem false assumptions. Now, in order to detect conflict between one or more lock requests, in this example that we have on the slide, there's already a write lock on G, which was a result of a write lock on two vertices G and H, and another thread is requesting a read lock on I, and that's a lock target, it's in pink. Without having to check whether there is actually a path between these two vertices, we just look at their integer ranges and see if they overlap. If they do, which 3, 4, and 4, 4 do overlap, then these two locks cannot be granted in parallel. So without traversing the hierarchy, we know whether one or more lock requests are going to conflict with each other. But there are still problems with DOM lock. First, even though we have reduced the number of traversals required to actually lock vertices in the hierarchy, we still need one traversal, which is for the search of an appropriate lock guard. Second is what I explained as false assumptions. And because these false assumptions enlarge the grains more than they should, these cause spurious blocks. And third is the inelasticity of this labeling scheme. And by inelasticity, what I mean is when a structural modification occurs in a hierarchy, for example, a thread comes along and tries to add an edge between H and I, we need to now update these labels to reflect the new topology. And because these labels propagate from the root to the leaves, this relabeling can only be done under a write lock over the whole hierarchy, which is equivalent to a coarse-grained lock, which allows no amount of concurrency, as we saw in the extremes. So a solution to this could be to again get rid of this search over the hierarchy by providing somehow an indexed access to vertices, by defining these log grains well enough so that they don't cause these spurious blocks, and third, making this labeling scheme elastic somehow. There's two more multi-granularity locking techniques, which I won't go into details of because they are extensions of DOM lock. First is what we call multi-interval DOM lock, and it tries to get rid of this property of this problem of false assumptions by keeping a pair of integer intervals for every vertex. One of these intervals is assigned by a post order from left to right, and the other is a post order on the mirror image of this hierarchy. So the first integer interval we see here, 1, 1, is because D is the first post order vertex in the post order traversal. And in this case, I is the first post order traversal on the mirror image of this hierarchy. But as you can see from the lock example grain that I have in this hierarchy, it still does not completely eliminate false assumptions because a lock on G still locks F because both of these ranges overlap still. Second is an extension that enables acquiring fine-grained and DOM lock on the same hierarchy. And it does that by, instead of storing two integer intervals, it stores integer intervals for DOM lock and a single integer that stores the level of that vertex in the hierarchy. For example, A is the root, so its level is 0, B and C have level 1 and so on. And by doing that, it can identify these false assumptions. Now, in the DOM-lock example, we saw that F and G were, we had no way of detecting whether F and G were actually connected. With FlexiGram, we know that because their levels are the same, so they cannot have an edge between them. If there was an edge, then F's level would be different from G. So it eliminates false assumptions to some extent, but but testing whether there is a conflict between this fine-grained log and this DOM log on A and G respectively is expensive because it requires a traversal. And my contribution tries to solve these problems. So it's called multi-granularity locking because that's the domain we are working in. And instead of using post-order labels, we use topology-based labels to identify lock rings. So instead of integers, we use sets of vertex IDs, which are IDs assigned by the system to those vertices. And instead of a post-order traversal, we use a path recursion from the root using this labeling function, which based on the labels of the parents, tries to compute the label of a vertex V. Now let's look at a working example. So it's the same hierarchy that we've been looking at in the last few slides. We start from the root because A has no parent. Its label is A itself. B has a single parent, so its label becomes AB. D has a single parent, so its label becomes ABD. And similarly, any other vertex with a single parent just takes the label of its parent and appends its own ID into that label. Any vertex with more than one parent finds the set intersection of the labels. So in this case, H has two parents, F and G. So we find the intersection of the labels ACF and ACG, and we see that the intersection is AC. And then we append H to that label to get the label ACH. And similarly, we label I. Now, if you compare the labeling of DOM-lock to CA-lock, we see that there was a single path that was followed to find the labels in DOM-lock, and these labels propagate from the leaves towards the root. Whereas for CA-lock, we have this branching of labeling. So a modification on any of these branches only affects that specific branch, which also means that we can relabel multiple branches in parallel. So in the presence of structural modifications, we only need to log that specific branch in order to be able to relabel the hierarchy. Now looking at lock acquisition, again, it's the same request. A thread is trying to lock G and H. Now, in order to find out the vertex that we need to lock to make these two to isolate these two vertices, we just look at the labels of the lock targets, which is ACH and ACG, find their set intersection and log the tail of the set intersection. So G and H have the labels ACG and ACH. We find the intersection that gives us AC, and the tail of this set is C, so we issue a write lock on C. Grain identification is even simpler. We start by looking at the labels of these vertices, and any vertex that has a label which contains the ID of the guard is considered locked. So after acquiring a lock on C, any vertex with C in its label is considered locked. So in this example, it's C, F, G, H, I, and J. Comparing it to the earlier lock techniques, we had intention lock, storm lock that I introduced. With intention locks, locking actually requires a lot of traversals that I've shown in as the path in red. With DOM lock, we eliminated some of these traversals and restricted it to just one search over the whole hierarchy. With CA-lock, you actually don't require any traversals because these labels themselves contain vertex IDs, which using an index, you can just directly issue a lock request. Now, in order to detect conflicts between locks, threads actually create lock requests that are added to a pool. So any active thread that's accessing something in the hierarchy would have a lock request in this lock pool that's shown in the example below. Each lock request contains 4 data points. First is the order, a sequence number that is used to denote the order in which requests arrive. And because they arrive in first come, first serve order, they are numbered so. Second is the kind of lock that that thread is acquiring. So for example, here we have G acquiring a read lock, B acquiring a read lock, and T3 acquiring a write lock on C. And along with this, it contains the information of the lock guard and its label. So T1 is requesting a lock on G, which has the label ACG. T2 is requesting a lock on B, which has label AB, and T3 is requesting a lock on C, which has the label AC. Now, using these lock requests, 2 threads are set to conflict if they simultaneously satisfy 2 conditions. First is a mode conflict, which is the classical form of read-write conflict. 2 write locks cannot be granted in parallel. And because we lock grains in the hierarchy, if a mode conflict occurs over overlapping grains, then it's actually said to be, then it's considered an actual MGL conflict. And 2 conflicting lock requests are granted in first come, first served order. So here in the example, T2 already holds a read lock on B, and it's highlighted in green, and its grain is highlighted in the hierarchy. And now there's 2 concurrent threads, T1 and T3, which are trying to lock G and C respectively. Now, between T1 and T3, we know that there is a mode conflict because T1 is requesting a read lock and T3 is requesting a write lock. Now, T1 is requesting a lock on G, which has this grain that I've highlighted in the hierarchy, and T3 is locking an overlapping grain that in write mode. In order to detect a conflict between these two, it's sufficient to check whether the guard ID of this lock request is in the set or the lock guard label of T1 and vice versa. So we look at the guard ID of T3, which is C, and see that it's in the label of T1, which means that these 2 grains overlap. And that's sufficient to identify a grain overlap. Now we know that there is a mode conflict. We know that there is a grain overlap. So one of these requests have to block, and this block is decided by the sequence number. So here T1 came first because its sequence number is 2, and T3 came second because its sequence number is 3. So T1 is allowed to acquire its lock and T3 is blocked. Now, if we look at how conflict detection happened with intention locks and DOM lock and compare it with CA lock, with intention lock, conflict detection happened during this locking process, which requires multiple traversals. In DOM lock, we had the problem of false assumptions, where vertex can sometimes cause its sibling or one of its ancestors to be locked, and this causes spurious blocks. With CA lock, this labeling function defines the grain well enough that it remains the smallest possible grain for a specific locking request. And we do not need these traversals to identify the lock conflict, which is why spurious blocks don't occur. Now, when a structural modification happens over the hierarchy, again, like any other labeling scheme, we need to update this metadata. And the same function that we used for the initial labeling step can again be used for relabeling. So we are again trying to add an edge between H and I. The new label of I needs to be recomputed because it's the vertex that's being affected. And the new label of I is computed by taking the set intersection of the new set of its parents. So I earlier had only 2 parents, G and J. Now it has one more parent, H. So we take their set intersection, ACH, ACG, and ACGJ, which gives us AC, and then we append the ID of vertex I to it. And that gives us the new set of labels for this hierarchy. Now, comparing it to DOM lock, because intention lock has no metadata, it does not require any relabeling. When we perform the edge update between H and I in DOM lock, these labels propagated towards the root, which means that we needed to lock the whole hierarchy so that no other concurrent thread uses those labels to then acquire a lock, which would then lead to ill-defined grain. With CA lock, this edge addition can happen under a localized write lock, which means that Another thread could come along, lock B, and perform a concurrent structural modification over the hierarchy. And that basically speeds up the runtime performance of CLO compared to other MGL techniques significantly. Second, these labels in DOM-lock propagated from the leaves to the roots, which means workloads which very often access vertices towards the leaves cause the root to be relabeled. Whereas with CLOC, we only need to relabel leaves and their descendants, which again allows us to relabel fewer vertices in the hierarchy and speed up the runtime performance. Looking at complexities of these locking approaches, for intention lock and DOM lock, they are both based on a depth first traversal over the hierarchy. So this is the average complexity of a depth first traversal. And here D average is the average degree of the vertices of the hierarchy. For CLOC, its labels are based on the set intersection of these paths, which is inversely proportional to the average degree. So as is evident from these theoretical complexities, for intention lock and for DOM lock, we might find them to be more suitable for hierarchies that have low average degrees, for example, trees. But CLOC really shines when the hierarchies are more complex because it's inversely proportional to average degree. To recall the potential solution that I stated at the beginning of the state of the art, we solve this granularity dilemma to some extent by having well-defined log trains that don't cause false assumptions. Because we do not need traversals for conflict detection and also by having indexed access through these labels, our conflict detection becomes much less expensive. And any metadata that we used for DOM-lock, multi-interval DOM-lock and FlexiGran is more expensive than that of CLOC. So we reduce the expense of labeling and relabeling the hierarchy. Now I've made a lot of claims about the theoretical performance of CLOC and how it's the best solution in the world. Now let's look at some actual benchmarks which back up the things that I stated in the last few slides. So these benchmarks were done using STM-Bench, which gives us a set of hierarchies and indices. And the workloads in STM-Bench can be configured on using three different parameters, which is having a read-heavy workload, a write-heavy workload, and specifying the proportion of structural modifications that happen over the hierarchy. In the chart in the charts that you're going to see in the further slides, all of these data points are a mean of 3 runs per workload per thread. So it's the average result of performance. And they were run on Grid 5000 on a machine with 48 cores and 512 gigabytes of RAM. And the implementation was specifically done at C++23 with optimization level 73. Now, the things that I want to basically benchmark was the different phases of this locking protocol. So when the system starts, we need to pre-process the hierarchy. So how expensive is it during the system start? On a hierarchy that has been labeled, what's its footprint in memory? So the size of metadata in the memory. Third is this relabeling of the hierarchy that happens when a structural modification happens. Fourth is this claim that I made about reducing false assumptions. So we actually compare grain sizes at different levels of the hierarchy to find whether we have actually eliminated them. And third is the runtime performance over static and dynamic hierarchies by measuring the throughput and latency. So starting with pre-processing. In this chart, you see 3 different sizes of the hierarchies, small, medium, and large, with the number of vertices and edges under them. And on the y-axis, we have the time it takes to label the hierarchy in microseconds. As you can see, CLOC takes on average 60 to 70 times longer than other MGL techniques because it needs to compute the set intersections for every single vertex based on the number of its parents. But the total performance limit of CLOC is still less than 0.1 second. So even for the largest hierarchy, it can be labeled in less than 1/10 of a second. So this performance is not that expensive. Looking at the size of metadata in memory, it's again 3 different hierarchy sizes, small, medium, and large. And on the y-axis, we have the metadata size in kilobits. CALOC's metadata, obviously, because it contains sets of vertex IDs, is more expensive than just storing 2 integers on every single vertex. And we see that it's about 47 odd kilobytes more in memory than other MGL techniques. Now, these two benchmarks, these two performance measures, the pre-processing step needs to occur only once, because it happens at the start of a system. And this metadata size is still in kilobits, so it's not that expensive for practical use. Now, where CALOC really shines is relabeling, which is a significant contributor to the runtime performance of a system. Now, in this chart, we have, again, the 3 sizes of the hierarchies on x-axis and the time it takes to relabel after a structural modification on the y-axis. And we see that CALOC is about 3 orders of magnitude faster than any other, than the fastest MGL technique, and about 5 to 6 orders of magnitude faster than the slowest MGL technique, which is MIT. So this 3 orders of magnitude and 5 orders of magnitude speed up really improves our runtime performance compared to other techniques. Talking about false assumptions, this chart shows based on the hierarchy that you see on the right, we have vertices of different types. So at the root level, we have complex assemblies, then base assemblies, and composite parts and atomic parts. So this chart shows these different kinds of vertices. So we have complex assemblies and base assemblies, composite parts, and atomic parts on the x-axis, and the number of vertices on average that are locked by locking a vertex of this type. So when we acquire lock using CALOC on one of these complex assemblies, on average, how many vertices are locked in the hierarchy is what I'm trying to measure here. And what we see is CALOC's label grains are typically, on average, about 30 times smaller than other MGL techniques. So not only is this labeling scheme much faster when we relabel the hierarchy, but it also leads to smaller grains, which means that we have less false assumptions, which correlates to runtime performance. Now, I want to present some charts about the actual runtime performance. Now, this chart has a number of threads on x-axis. The vertical line that you see here is the number of cores that were number of physical cores that we had on the processor where we benchmark. And on the y-axis, we have the throughput in million operations per second. Now, coarse and medium locks are 2 static locks, where coarse lock is just a root lock on the hierarchy, and medium lock locks every single level. So by locking a complex assembly, I lock all complex assemblies. Now we see that coarse and medium locks have very stagnant performance, which doesn't improve as much as the number of threads in the system increases. With intention lock, because of the amount of traversals that we need to perform in order to lock vertices, its performance really takes a hit when we deal with hierarchies. For DOM lock and multi-interval DOM lock, its performance is much closer to coarse locks for hierarchies, and it goes up to about, it increases up to about 8 threads and then takes a hit for workloads that have very high contention. FlexiGran is very similar to intention lock because the amount of time it takes to compute a conflict between a fine-grained lock somewhere in the hierarchy and a DOM lock is very high because it involves performing a reachability test. CALOC shows poorer performance compared to DOM lock for workloads that don't have as much contention, but when we reach into the territory of high contention workloads, then CALOC really shines. Now this is for static hierarchies. So we still do not have any structural modifications happening in the hierarchy. For other workloads, the chart that I showed you in the last slide was a read-heavy workload. On this slide, we have a balanced workload with 60% reads and a write-heavy workload with 10% reads only. And we see that CALOC shows consistently better performance than other MGL techniques in workloads that have high contention. For latency, these charts show the number of threads and the lock latency, which is the amount of time that passes between when the lock was requested to the time when it is actually granted. And we see that the lock latency for CA lock is better than any other locking technique. Now coming to dynamic hierarchies, where we actually have structural modifications happening. It's the same chart as we had seen earlier, but and this workload is now a read-heavy workload with 0.1% structural modification. So 1 out of every 100th operation is a structural modification. On the y-axis, we again have the throughput in million operations per second. So we see that coarse and medium locks perform as they did for static hierarchies. Intention lock is the same because it involves a lot of traversals. Now DOM lock, multi-interval DOM lock and FlexiGrand show almost zero performance because of this mutex that you need to take on the root of the hierarchy. And as soon as you take a mutex on the root of the hierarchy, you basically block any other operation. And that really causes their performance to suffer when dealing with dynamic hierarchies. And CA log shows the performance that it did for static hierarchies as well. So it remains better than any other MGL technique for dynamic hierarchies and better than any other locking technique for workloads that have high contention. Now looking at other workloads, on the top we have throughput charts which show read heavy, which range from read heavy workloads to write heavy workloads on the right. And these workloads contain at minimum 0.1% structural modifications to at most 0.9. And even with this small percentage of structural modifications over the hierarchy, we see that all of the other MGL techniques really take a hit. And even in the presence of structural modifications, in the latency charts, we see that CA log's latency remains lower than any other MGL technique. So the problem of solving false assumptions, the problem of relabeling the hierarchy, and having high runtime performance are the three claims that I made when I showed the challenges of MGL technique. And through these charts, I basically tried to show that we actually achieve them to some extent. And that brings me to the conclusion. So in the presentation, you saw two contributions. First was this labeling scheme based on these recursion, based on this recursion from the root to the leaves. It's efficient because we provide indexed access to the vertices, thereby we eliminating the need of traversals. It's extensible because this relabeling can be done in parallel and it affects fewer vertices compared to other MGL techniques. And we saw in the performance benchmark that it was about 4 orders of magnitude faster. These grains were well defined, so they cause less false assumptions and consequently less spurious blocks. And we saw that they lead to about 30 times smaller grains on average in the hierarchy. The lock protocol gains efficiency compared to other MGL techniques because it eliminates the need of these traversals, both for locking and during conflict detection. And we see that it's about 4.5 times faster than other MGL techniques and gives about 100 times lower latency. And because we grant these locks in a first come first served order, CA lock remains fair. Now the two domains where I see CA lock actually being applied are both in searching connected data using the labeling scheme that we designed, which enables us to find the lowest common ancestor of a set of vertices efficiently. So if we just talk about the labeling, it can be used for deep hierarchical data. For example, the chart that you see on the top right is a phenotype graph for human diseases. And a very common query for these kinds of charts is to find the lowest common ancestor of two phenotypes in order to identify the cause of that disease. Second is when we are dealing with object-oriented languages, then we have these inheritance charts. And a very common thing to save resources is to perform dependency injection on runtime. So based on the classes that we are going to initialize for to run a specific program, we can perform a minimal dependency injection by finding out the lowest set of dependencies that needs to be initialized for a specific class, and also use it for service lookup. For the synchronization mechanism or the locking mechanism that I showed can be used in not independently of the labeling. CA lock still needs its labeling, but it can be utilized with that labeling scheme in a variety of domains. The first is, for example, scheduling systems. And the chart that you see here is used to compute the probability of somebody defaulting a loan when they go to a bank. So the bank runs complex graphs like these to find out whether a person who's taking a loan is not going to pay it back. And the labeling scheme here is used to find out the smallest set of dependencies that need to be scheduled in order to run our program. And based on these minimal set of dependencies, we can book resources over our cluster to then make sure that these tasks are executed with minimal preemption. And that saves both on computing resources as well as because these steps individually generate huge amount of data, we save on storage space as well. Second is the actor model, which is a very common programming paradigm for distributed systems. And a very common problem with actor models is to find an actor where we need to synchronize several different operations. The chart that you see on the right is the actor hierarchy for Antidote DB. And if, for example, an operation occurs between these 4 actors, we can use our labeling scheme without having to do any kind of lookup to find out the actor where this needs to be synchronized. And by judging the actor where we need to synchronize a set of transactions, we can provide atomicity more easily. And that brings me to the end of my presentation. This slide lists out the things that I discussed with a summary of the results. Thank you.
Thank you. So we'll start with the reviewers, and we will start with Pascal.
Thank you. Well, thank you for the nice presentation and the nice manuscript. Actually, I really enjoyed reading it because it's not too long. It's really self-contained and it goes in deep on a given problem. But of course, I have some questions regarding. I mean, not so many details, but more about the prospect of how to use that, how to exploit that, because you're really addressing a very focused problem of locks, dealing with locks in some specific type of data structures. I mean, the first of this question is you're dealing with the hierarchies. When I started reading, I say, oh, he's going to test on a graph database.
Oh yeah.
And then I was kind of a bit, let's say, surprised to not see too much of graph databases discussed in here. So as a first general question, just to put things in context, how would you directly apply that to an existing graph database? What is the prospect of using it?
Okay. We actually did an implementation with the graph database. I don't think I have the slide here, but we measured. So I did an implementation with Tinkerpop, which uses Gremlin to implement a database, and I directly took this labeling function and applied that to Tinkerpop and measured the performance. And what I saw was a very fundamental restriction of hierarchies, which is that they need to have a designated root. And in order to get around it, what I did was to superimpose or to split this graph into multiple ones where every single subgraph has a single root so that they can be labeled independent of each other. But the performance really was poor. So the performance of using CA-lock in its current form over graph databases is equivalent to taking a read lock over the whole graph, which is not very good. So another solution that I thought to be able to speed this up was to actually use the workloads that we have in the graph, and I could not do this because of the lack of time. So we know that workloads are not uniform across all vertices. Some vertices in graph databases are accessed more often than others. And we can make use of these kinds of vertices to actually start the labeling step from those vertices so that the most accessed vertex is labeled with the most optimal label, and that would consequently lead to higher performance. But because it's a graph database and I need to benchmark it with huge amounts of data, I could not do it because of the lack of time.
Okay. There could be some potential here,
Yes.
given you have time. So another this question I had, I've been working a lot on transactional memory, and you're using STM Bench 7, which is also something coming from the TM scope. there are like a number of techniques in the database community to exploit also hierarchies.
Mhm.
Like if you have transactions, you have tree locking protocols that have some of the kind of same ideas. You have like an order in which you try to do the 2PL
Yes.
positions of the logs in a tree-like order, and you don't talk much about transactions.
Mhm.
And this was one of my obvious questions. Why not take this and apply this to some kind of transactional memory systems in which you can get the logs in the right order to then do a transaction?
So the reason I don't explicitly use the word transactions is to avoid basically the confusion between accessing data and what it means in terms of atomicity and then multiple transactions doing, for example, two-phase locking. These operations that I said that threads can perform on a hierarchy are transactional. You can execute them in a transactional workload. But the restriction here is like two-phase locking, where you can only take locks, and once you release one, you cannot take any more locks. In this CA lock or any other multi-granularity locking for that matter, you have to know your read set in advance. So you lock everything at once, perform your transaction, and then release the lock at once. And that's simply to facilitate the use of a single lock. So that's an assumption that multi-granularity locking works with, that all of the threads know their read set in advance, or at least know a broad range of their set, because the grain basically contains several vertices. So if I know the maximal range of my access, then that's the thing that I lock, and it can be used in a transactional context without any change.
Okay. So talking about read locks and write locks. So you have you support different mode of acquisition for locks. And you talk about fairness as well. What is your fairness condition when dealing with read and write locks?
So we don't skew reads over writes. It's just first come, first served. But it can very easily be adapted to, for example, favor readers over writers, or favoring writers over
But
readers.
can you have a reader? Can you have a writer never get a lock because there's always some new reader coming later?
No.
Because you always have this problem that if a reader comes later, the writer is blocked, but the reader doesn't conflict with an existing transaction or an existing, let's say, thread, then it can kind of overpass the waiting writer because the lock is free in read mode. And then if you have this flow of new readers coming, you can essentially have a writer waiting forever. Is it something that can happen or not?
So thread starvation doesn't happen with CA lock. And that's because as soon as a thread requests a lock, it's given the sequence number.
Okay.
And if a reader comes along after a writer had requested its lock but not actually acquired it, the reader would have to wait until an earlier lock request is granted first before it can be.
So you let the readers drain out before the writer gets in. Okay. Good.
So readers don't bypass writers waiting for.
I was just wanting to double check that. That's good. How about do you deal? I don't. So the locks are not preemptible. You assume that like in this question, what happens if a thread fails to release a lock? There's a failure. There's an exception.
There's one interesting trick with all of these MGL techniques, where we actually don't acquire a pthread lock on the hierarchy itself. It's just this lock pool where all of this happens. And it's called multi-granularity locking because of the classical use that intention lock started for the word. But with DOM lock, multi-interval DOM lock, FlexiGran, and CA lock for that matter, we never actually acquire a physical lock on a vertex. It's only this lock pool where this scheduling happens, where threads detect conflict, and if there is a conflict, they just wait on that lock pool instead of going to the hierarchy and waiting on it. And because this whole conflict detection happens on the lock pool, we can have exponential backoffs or thread helping, for example, to make sure that if a thread died, for example, it has not released its lock in the last 10 minutes or so, then another thread can come along and say, okay, I consider this thread dead. And this lock pool in our case contains unique entries for threads. So thread T1 always inserts its lock request at index 1. So I know that if T1 comes back and requests another lock, it's not going to have an existing lock request somewhere else in the pool, which is basically blocking everything. Okay. So it will replace its old lock request with a new one.
So you mentioned thread helping. How about lock-free algorithms?
As far as I know, there's one lock-free algorithm that works over graphs, and it uses double collects. So it performs one scan over the hierarchy, makes its updates, and then performs another traversal to find out whether its updates were correctly performed. And when it detects a failure or detects an inconsistency, then it rollbacks its operations. But this quickly becomes expensive because when we are performing double collects, we don't know when this double collect is going to be stable. So we could be performing traversal over traversal and then also leading other writers to block, because you cannot have a writer modifying something during a double collect, or then your double collect result is violated. So then that leads to this condition of I expect that at some point nobody is going to write to the hierarchy so that my double collect becomes correct, so that I can validate my set of updates. So there's this big assumption that there's going to be a quiescence point in inconsistency.
So in your performance evaluation, we see that you get quite a hit in performance from the preprocessing phase. So is it mostly due to the set intersection computation or the additional, let's say, space required to do the management of the or the bookkeeping of the vertices?
So
the
in the pre-processing step, we are not doing any additional bookkeeping. So the indices or every other kind of auxiliary data structure is separate. The pre-processing performance is a raw measure of, I start my labeling step, how long does it take for my thread to return that it has actually labeled the whole hierarchy. So it's only set intersections that causes
because you need essentially to check the sets and do the combination.
Yes.
Yeah.
So it's complex because we need to perform set overlaps.
Yeah.
So every single time I navigate a path, I perform a set intersection. And because we are not dealing with acyclic graphs, I have a huge section about strongly connected components in the manuscript. Because we don't restrict the topology of the hierarchy, we have to make sure that every single path is encountered when relabeling a vertex. And any time that one of these ancestors changes its vertex, we have to change the label of the children as well.
And you use some tricks, for instance, let's say, you can do set intersection with Bloom filters. You know that you have some false positives sometimes, but it doesn't matter if you sometimes detect that there might be a conflict and you don't, well, there's a trade-off. As long as you don't have false negatives, it's okay. Could you use these tricks?
Yes, definitely. But the reason I don't have them in the implementation is because the raw performance for even the largest hierarchy I saw was less than 1/10 of a second. It was like, okay, I mean, if we gain maybe 0.1 second using Bloom filters, then it's not really computationally as as attractive.
Makes sense. So I have I will soon to you. But let's say one last question. When I started reading the thesis, when I looked at the introduction, saying, okay, the consistency is very important, the distributed data structures are omnipresent. And knowing, of course, that you're working with Mark, I was wondering, oh, this should be some distribution, there should be some CRVT in it. And I was seeing some potential for these techniques in distributed settings and also in providing, like improving some kind of CRDT-based data structure that you could provide to other developers and, with nice properties. Did you look into that, and how could you take what you have and use it in this context?
Yes, this whole work started with CRDTs in mind,
Okay.
because we were studying one of the old PhD thesis, who the researcher is sitting in the room, Shrija. So I started with her thesis, and we were studying how we can coordinate these operations over a CRDT that conflict. And because these operations form a lattice, I encountered this problem of finding the order in which these conflicts need to be resolved over a CRDT. And that led me to the problem of finding these common ancestors of vertices. And I've made a detour to then apply it to locking, because that felt like an interesting idea. So it's of course applicable to CRDTs, and that's where this research started from. But we left it unexplored for
Another PhD.
taking another topic. Yeah.
Good. So thank you very much. I think I took enough time, and I left some questions hopefully for you guys. Very nice work.
Okay. So, David.
Okay, thank you very much. So, yes, it was a great pleasure to read your manuscript. First of all, I would like to congratulate you for the nice presentation that you did. It was as pedagogic and clear as in your manuscript, and one more time, I deeply appreciated the way you structured your manuscript, and you defined really well the context, the background, state of the art, and also the comparison with the state of the art and your contribution. And this whole story was pretty nice and to read, and deeply appreciated it. Thank you. So I'd like to congratulate you for that. So now, of course, I have some questions. My main thinking was how to apply more concretely what you have done so far. What is interesting is that you did this effort to do theoretical contribution as well as an instantiation, a concrete instantiation to evaluate it. But the thing is, I'm really curious to have your point of view about concretely in which kind of true system you can instance it.
So one avenue where I was really, and I kind of regret not exploring it sooner, was applying it to MongoDB. And the reason I could not do it for MongoDB is because, first of all, I was just one individual developer and I can't write a whole database on my own. Second, the storage layer in MongoDB is handled by WireTiger. And in order to basically unify the transactions that MongoDB has with the storage layer that WireTiger implements, and then basically fixing or bypassing all of its storage tricks in the form of indices. So for example, MongoDB doesn't always write to the disk when transactions execute. That was basically a computationally, but implementationally more expensive for me to do individually. So that is something which I'm still exploring. I want to get it into a database. The first target was JSON, but MongoDB, but that didn't happen. I did another graph database implementation. That didn't lead to good results because it wasn't unexpected. I expected it to show poor results for generic graphs. But yeah, it was JSON where I really wanted to implement it, but just because of the lack of time, I could not achieve it.
And you were working the fact that, yes, MongoDB is doing some part of it in memory, but if you are targeting directly the storage engine without using the whole block of MongoDB, but just the small part of it that's stored on file system, do you think it's doable or in a reasonable time to apply your approach?
I think it is, but what I'm not sure of is how expensive would it be to then perform this translation from a concrete data representation of this JSON object that we have in memory to then a different list or a set-based representation that we have on disk. And in all of the benchmarks that I have, they are in memory, so the hierarchy is not actually persistent on the disk because its size is relatively small. It can fit into 512 gigabytes of RAM. But when we have this, for example, loading of the data from the disk and then the disk, loading from the of the data from the disk into memory, and then the memory becomes full. So some of my vertices that I actually want to lock are not on in the memory. Then we have to deal with all of these faults that come from memory not being available. It's this translation between this in-memory representation to the on-disk representation of the data that I'm not sure of. But it can be applied. I'm sure that it can be done, but it's just that I'm unsure of this step of translation of this conflict and labeling process, for example.
That's very interesting because at the same time, when I was reading your manuscript, because you are leveraging mostly on autograph, right? So it's still very hierarchical, and
Yes.
most of the time it makes me think to a file system.
Uh-huh.
And so far I was thinking about, okay, does it make sense, for instance, for a file system?
Yes.
Because then, manipulating a file system or instantiating these kind of things, with logs on files and etc., it's much easier than a database.
Yes, definitely. CALOC would actually be, in its current form, completely applicable to file systems. But I don't think it would give you an advantage over other techniques. There's more efficient ways of making sure that file systems are consistent.
Yeah.
So while it can be used, I don't think it's a good area to
It's a
use
good
it.
area to be used. All right. Okay. But
It's simply it's simply because the amount of operations that we actually perform on a file system don't go into million operations per second, which access random parts of the hierarchy.
But there are also some graph-based file systems that are emerging, which is quite different from the regular ones. And so for this one, do you think that should make sense?
For graph-based file systems, I'm actually not familiar with graph-based file systems, but if it's the fact that locking multiple directories or files should remain atomic and isolated, then yes. You can use CALOC as a technique for making sure that inconsistent access to that file system doesn't happen by either implementing it on top of that file system directly or just by using it as an auxiliary scheduler of threads over that grafted file system. So the only constraint that CALOC has is that graph has to have a root. It doesn't care if it's cyclic or not. It doesn't care if it's complete, non-complete, whatever. The only constraint is having this root, which file systems always have a root. So it's applicable.
It makes me think also that what happens if you consider a graph and you want to change the root? So I don't know, first time you may want to attack the graph in different perspective, and then you want to change the root. The root, for instance. So do you think that it's doable, or what will have as impact on your algorithm? Because if you change the root, but still let the lock that you have done for the previous root, what kind of impact do you have?
If there's already an existing lock on the old root of the hierarchy, then that new root cannot be added because that new root's grain would overlap with the whole hierarchy. So in order to add a new root, we first add that root as an individual vertex. That's correct on its own because it's not connected to the hierarchy, so it doesn't matter.
Yeah, sure.
And when we add an edge, when we add an edge between the two, at that point we lock the old root and the new root together in a big grain, and then add that edge and then relabel the whole hierarchy. So it's like any other structural modification. It's just that the relabeling step would be more expensive. But I mean, we assume that it's going to be expensive because we are changing the root of the hierarchy.
Okay.
So it would be correct, but not maybe as performant as, well, not performant. There's no comparison to anything else.
In your evaluation part, I was quite surprised to see that in terms of output, you start to have very good performances after 16 threads. So, first, I would like to know why you have this kind of performances. Why
So-
after 16 threads and not before, and why you are better and better, more you are adding threads?
So the reason CLOC improves on workloads that have more contention is the amount of time it takes to lock. So it's actually the lock latency that ends up improving our performance. So when we have a higher number of threads, they are all issuing lock requests. For example, if there's only 8 threads in the system, the lock pool contains only 8 entries. And then those threads are basically iterating in different orders over the log pool to find conflicts. Now, because with other techniques, our grains are bigger, means that a thread keeps waiting on these individual entries in the log pool to acquire its lock. But with CLOC, it's actually the set intersections that bottleneck the system before 8 threads. So when we are locking multiple vertices, and in the throughput charts, it's not just one vertex that we are locking. Those lock requests sometimes contain 50 or more vertices at the same time. So the expense of computing these 50 set intersections, even using boost sets, for example, in the implementation, is more expensive below 8 threads. And when we go above 8 threads for the same 50 lock requests, we run into a performance improvement because multiple threads can do these operations in parallel.
But so it leads to another question is, if I have a resource constrained device, then I should not use your solution.
Yes. There's no denying, yes. It's not something that you would use for a memory constrained device. So if there's constraints on memory because our labels are more expensive, then it's not a good idea to use. Unless
Not only on memory, I mean, even if you have a small resource constrained devices with huge amount of memory, but few amount of threads or cores, then you show the evidence that should not scale. But for your point of
Yes.
view, it's more memory constrained or?
it's more memory constrained.
Or
The
thread
reason it shows poor performance for a fewer number of threads is because we haven't optimized the set intersection. So if you can optimize, for example, we use boost sets, but you could as well use Bloom filters, for example. That would improve this performance by giving you a true negative very quickly. But then if there is a false positive, then you might have to traverse the hierarchy. So by using some of those techniques, we might be able to improve the performance of this system. But what I'm thinking is whether it would actually cause it to be better than other MGL techniques. I think not still. So with let's say only 4 threads in the system, we might have fewer blocks. But the cost of locking with DOM lock or multi-interval DOM lock for that matter would still remain low because threads can keep waiting and then lock bigger grains in the hierarchy. So for resource constraint system, although it's an interesting idea, I think I should explore it further. I'll run more benchmarks on it.
Did you explore different kind of lock or like spin lock or something like that? Or because you explained that it takes time in terms of taking locks, etc. But there are different variants of lock. Do you think that?
Yes. So I tried,
change,
I tried both variants of locks. One was spin or busy waiting locks and p-thread locks. And with spin locks, as we had expected, it takes longer because a thread is busy waiting, and it does not. So it does not lead to a performance hit when we have more cores available than there's threads in the system. But as soon as we go into the territory of higher contention, then we get a performance hit. But then when I analyze the system more, I actually realize that we never test for conflicts on those pthread or spin locks actually, which is why I explained earlier that we actually don't acquire any lock on the hierarchy. It's just the scheduling that happens on the lock pool. So the cost of this locking is not actually the cost of acquiring a pthread lock or a spin lock using the system lock primitives. It's just the cost of scheduling, which is finding a set intersection when there's a conflict. You wait on that thread in the lock pool, and as soon as that conflict resolves, I know that there isn't going to be any further conflicts because my sequence number is going to be the lowest. So then I can just make progress without testing anything.
Yes, this aspect I think is missing. I mean, when we read your manuscript, we want to know more on the low level details. And so, this is something that you should also highlight in order to, because you did this work at the low level perspective, and so it should be very interesting to get it.
Yeah.
Also. Okay, and yes, I had a similar question as Pascal because I was expecting also CRDT in somehow to see some or distributed part of your work, and so in a distributed system, do you oh, I had another question. Yeah, it was quite related to the subsystem, but if you have a malicious thread, you have a thread that always wants to take lock. I don't know, close to the root or in the middle of the graph. May we lock all the other threads? If I intentionally do a thread that try to take locks,
No.
to lock the other,
No.
do I, may I be able to do it?
No. The reason is because the sequence number are assigned by the system. So while you might create a lock request, while you might create a thread that always requests a lock on the root, it would still be scheduled in a fair order. So if there's multiple threads already waiting, then it would get the last sequence number. So it's this assignment of sequence numbers that really makes sure that starvation doesn't happen.
So say if I spam the system of request lock.
Yes. If you hack the system, then you can do anything.
No, but just sending lot of request lock on the.
No. So a single thread,
or,
a thread can only request one lock at a time.
Okay.
So because it has a unique entry for itself in the lock pool, it can request a single lock at a time, and that lock could have an arbitrary size of the grain. So if it wants to lock 50 vertices, it just locks the lowest common ancestor of those 50. But it cannot issue multiple lock requests one after the other.
Yeah. Okay.
So DDoS attacks are it's robust against those.
Okay. So that's it. I will let my colleagues do some questions also.
Thank you.
Thank you very much.
So we will continue with the examiners. So I don't know if you can hear me, Satya.
Yes.
Okay.
I can.
You can ask questions.
Yes. I hope you can hear me and see me. Or something happened to my video.
Don't
Yeah,
see you.
anyway.
I will go to the Zoom call.
It was not working. You can hear me, right?
Yes. Perfect.
Yeah, yes. Yeah, the system, my video is not working. Anyway, so I had few questions, but they were already asked by the previous examiners. Okay. So let me ask one very basic question, simple questions in the interest of time also. Ayush, you had mentioned that the correctness, consistency you had mentioned, but you didn't specify what is the consistency or the correctness criterion that you were considering
Do
in your setup. Yeah,
do
go
you mean
ahead.
the consistency level of
So in the initial part of your presentation, you said that the logs were not correct, the consistency will be violated.
yeah, so the
What do
thing
you
that
mean by consistency here?
okay. So by consistency, I mean the level of consistency here is serializability.
What serializability? The different notions of serializability, right? View
So
serializability, conflict serializability, they have different meanings.
Yeah, but those arise when, okay. So the thing that I want to say about consistency here is that when a thread is accessing a set of vertices throughout the duration of its access, so it's let's say trying to update data in 50 different vertices, I guarantee that at no point during this sequence of updates, there's going to be another thread that updates one of these vertices. So it's actually isolation that I achieve, but by locking things in a transaction, it ends up being serializability in the database sense of serialization.
Okay, database has different notions of serializability, you should qualify.
Yeah.
So maybe what you mean is conflict serializability, I think.
Yeah.
Okay, so it is conflict serializable is also view serializable. Okay, probably that is what you're intending, I can think. Okay, we can try to get this clarified later. So this is one question. The other question is you had mentioned the cost of locking.
Huh?
Okay. In your presentation, you mentioned there's a cost of locking, and that is what you're comparing the different blocks. So here, the cost is is it going to be throughput in your analysis, or is there are other metrics also it showed? Can you go to the slide in which you're comparing the different blocks?
The static ones or the dynamic ones?
Not the results. Before the results, you had a expression. For the results section.
Do you mean this one?
Yeah, this is one other thing. So this is the complexity of obtaining the lock.
But
Yeah. So what is this? What are these numbers actually represent?
so with all of these techniques, we have this labeling step that needs to happen. Okay, so we first need to find out where we need to lock in the hierarchy, and that's the middle column, which is this log guard computation. And okay, I don't have
So
a
this
pointer.
is in terms of number of the runtime analysis.
Yes.
Okay.
So it's
Okay.
for downlock, it's proportional. It's basically the complexity of a breadth first traversal over the graph.
Hmm.
But
Okay,
with
and CA lock. Okay. So
it's
my question is, this is what you mean by the complexity of a lock? Apart from throughput is the one that you did the experiments, right?
when I say cost of locking, I don't just talk about this computation of lock guard. The cost of locking actually involves a few things. First is this expense of actually finding out where you need to take a lock. And for example, with intention lock, it could be performing that traversal from the root to different lock targets. And then there's a second cost, which is part of the total cost of locking, and that's the cost of detecting conflicts. So when I say locking cost, it's the total cost of finding out where you want to lock, actually taking a lock, and then also finding out whether there is a conflict between different lock requests.
Okay. So it is basically the time taken. Okay. So essentially, ultimately, what matters is the time taken for obtaining the lock.
Yes.
That's what. And these are the individual subcomponents of these.
Yes. Well, the last two columns, labeling is not part of taking the lock.
Yeah. And that is so you're basically in the performance metric in the experiments, you're measuring the actual throughput,
Yes.
right? Okay, fine. So that's what you mean by cost. And so the other question, so one more simple question. So what you showed is a hierarchy, and you're telling each node is having a parent, but in the way it is shown, it's actually a directed acyclic graph. A node could have multiple, like, I don't know, a node could have multiple incoming edges, right? So then if that happens, that is going to complicate your computation. Right. So here in the figure that you've shown, only two nodes have multiple incoming edges, but in reality, there could be multiple incoming nodes. Multiple nodes could have incoming edges. And is it also possible that you had mentioned the term root? Okay, so root means one single node, the node that doesn't have any incoming edges, right? Is it possible that you could have multiple roots in your analysis in the hierarchy that you're considering?
So in the experiments here or the description here, we don't have hierarchies with multiple roots. But see, there were implementations that I haven't explained here that we did with hierarchies that actually have multiple roots. And in that case, CLOC labeling actually looks similar to multi-interval DOM-log, where each vertex now has multiple labels, one corresponding to every single root. So if there's 5 roots in the hierarchy, every single vertex would get 5 labels because it's essentially
So will that complicate the will your experiment analysis still be similar, or is it going to get more?
No, it would be more
Is it going to
expensive.
be expensive, right?
Yes.
And will it be the same for other competitors?
Yes, because with DOM-log, those labels propagate from a single root. So it would be, if there's 5 roots, then we would have 5 post-order traversals, each from every single root. So we would have 5 integer ranges per vertex.
So it's also expensive there.
But actually for hierarchies that, your previous point about hierarchies that have multiple incoming edges, for complex hierarchies, CLOC actually gives better performance. Because
you tested that?
Yes. Because for complex hierarchies, and even in the theoretical complexity, it's for complex hierarchies with high average degree, our theoretical complexity also is inversely proportional because our label sizes get smaller as we have more parents.
But then having multiple source nodes, roots also increases the complication, right?
Yes,
it depends on where, at which level you have how many multiple roots. So in the sense that if the number of node higher up is having multiple incoming edges, multiple parents, then the cost could be higher.
No, the cost would still be lower.
Only in the case, but then you just mentioned there's the multiple roots. For each of them, you have to do a traversal. That is going to increase the cost, right?
So only having multiple roots causes this data structure to not be a hierarchy anymore. It becomes a graph. So for graphs, it gives poor performance. But if it's a hierarchy where we know that there is a single root, then a more complex hierarchy performs better with CLOC than with DOM-log, multi-interval DOM-log, and FlexiCran.
So only in case of non-hierarchies, the performance is bad. As long as it's hierarchy, that means a single root. But every other node could have multiple parents, multiple incoming edges. It performs well. Is observation. Okay. Well, yeah, probably should stop now in interest of time. Last question is this: the actual implementation. How did you actually implement it using? Did you told me that you didn't use p-thread locks or other locks, right? So how did you actually implement that?
It's just based on blocking threads. So when we detect, there's this lock pool that I talked about in the presentation, and all of the threads, when they request a lock, they iterate on this lock pool from left to right. And that's just so we maintain this deterministic order of conflict detection. And anytime a thread detects a conflict, which essentially involves checking set membership between a guard ID and a guard label, it blocks on that entry and waits for a notification from the thread that's actually blocking it. So if T1 blocks due to a conflict with T2, it waits for a thread notification using this atomic weighting primitive that we have in C++23. And it waits on that notification. As soon as it receives it, it proceeds further in the log pool to detect other conflicts.
So are you Intel using conditional variables to implement this notifications and so on?
So it's conditional variables and atomic weighting on those conditional variables.
Okay. So in the actually it'll be the should probably be nice if you can see the GitHub code of this. I think the link of GitHub is there in your thesis, right?
Yes, it's open source. You can go through the code.
Is it? So and what is the cost of this lock acquire and lock release? Did you measure?
What do you mean?
When you so like I'm assuming does this have the lock acquire lock release syntax? Like
Yes.
normal locks have acquire and release, right? Similarly, you do have acquire and release here.
Yes.
So the cost that you measured is all for lock acquire, or what is it you're measuring?
It's the cost of locking is the cost. It's both acquire and release. And in the charts that you see in the throughput, the operations that's done between this acquire and release step is basically a no-op. So it doesn't take any CPU cycles that would skew results in terms of throughput or latency. So when I say the cost of locking, it's actually both acquire and release.
The sum of that. Okay. So you're not separately computing lock acquire, lock release.
Actually, release is not that complex. Release only involves sending a notification of completion to all the blocked threads that are waiting on that thread that's releasing its lock. So the major cost in the part of the cost of locking is actually the acquisition step and not the release.
Fine. So I'll stop now. I have a few more things, but maybe I'll discuss with you later. In interest of time, I have to stop. I have other meetings. So thanks to the jury and everyone for giving me this opportunity. Yeah, thanks. I'm here.
Thank you.
Great, thanks. So, Stefania, you can ask your question.
So first of all, thank you very much for giving me the opportunity to join your thesis defense committee. The thesis was very, very well written. It was a pleasure to read it. And I wanted to commend you on your maturity and your level of expertise, because I also had the pleasure of working with Ayush. And yes, he's an expert in his field and very nice to work with, on top of everything. So many of the questions were already asked, but I'm going to insist on the graph database part for obvious reasons. So how could your approach be extended to support richer models, in particular property graphs that are multi-graphs, multi-labeled, and in which you can also have these attributes on p-value pairs on edges. So at the level of the data structure already, how could you envision extending your work to support property graphs and RDF graphs?
So the database implementation that I did with Tinkerpop, it's actually based on a property graph. And the way that CAlog extends to graph database is by treating those edge labels, which in themselves are entities. So instead of saying we lock vertices, we now with graph databases say we are locking entities. And that could be a vertex, that could be a key value pair within a vertex, or it could be a label on an edge. And that's because of this representation of label property graphs in memory, which says if there's an object, whether it be a vertex or an edge, we don't care about it, except that object has some properties, which could be of type label or of type property. So these entities are treated as the low-level objects that we are going to lock instead of calling them a vertex.
So all the functionality is there to actually support
Yes.
this. Yeah. So talking about the operations themselves, so if you were to compare what you can currently do to what people can do in graph databases, particularly at the level of the query language, that is quite advanced. So now we have Cypher, Gremlin, GQL, SQLT, GQ. So these modern graph query language actually mix pattern matching and complex graph traversals. So how could you support this beyond the CRUD operations?
So the supporting pattern matching and other complex queries for that matter is just translating them from that representation of a query, for example, Gremlin or SQL PGQ, into this traversal. And that's something that I did when I did a Tinkerpop implementation. So a complex read query that could be a pattern match or a reachability or betweenness centrality for that matter, anything of that kind, just involves traversal over the vertices. And in that sense, it is sufficient to lock the source of this traversal because reachability is only going to be answered when there's a path. And by locking the source, I guarantee that I lock that path.
But what happens when you have graph queries that are, combinations of paths? Like, unions, transitive closure on top of paths.
But they are always translated to these
Okay,
individual
translated,
traversals
okay.
over the graphs.
So what happens with multi-hop graph queries that might potentially involve spanning multiple subgraphs? How do you ensure optimal granularity in that case?
So optimality of granularity is dependent on the topology. So if my traversal is so big that it encompasses a lot of subgraphs, then I end up locking those subgraphs.
Okay.
So it's both the kind of traversal that we are performing. If it's going to be a search, for example, on a local subgraph, then it's sufficient to just lock some part of that local subgraph and not cause a block for threads over that large supergraph, for example.
So I have another question regarding your experimental analysis. So I really enjoyed reading that part of the thesis, but I was actually wondering if you also did some experiments on real world graphs using, for example, Snap or Connect or
Yes.
LDBC, because the graphs that you presented were synthetic.
Yes, so I have experiments with the Snap dataset. I remember I did it with the G-Nutella graphs that the Snap dataset has. But as I already explained, the results that we saw with graph databases using CLOC in its current form don't give that good of a performance. And that basically gave me the idea of using this skew of workloads where we know that some vertices are accessed more than the others. And semantic, another thing which I didn't mention in the presentation, and I think it's in the manuscript, is the semantic differentiation of non-conflicting operations, which is something we take from CRDTs. So if two queries operate on the same vertex, but they are updating different key value pairs, then while they topologically conflict with each other, which would be a conflict with CLOC, semantically they don't. So these kinds of operations based on workload analysis can be used in actual graphs to improve performance.
Okay, so very nice that you talked about workload analysis. How about schema analysis? Because increasingly graph systems are becoming schema aware. So how would you leverage this information to improve the efficiency of your system?
So with schema analysis, one thing that I see happening is knowing the fact that some parts of or some subgraphs are independent of each other based on the schema. So they might be in, for example, different schema objects that are never accessed concurrently, which means I actually know that they don't require synchronization via locks. So I can bypass the whole locking step and say there's never going to be a conflict here. And that's because there's this schema definition that I have.
So you can render your approach also schema aware.
Yes.
So how about supporting your approach in graph databases like Tiger Graph that are hybrid OLTP OLAP, where you mix analytical and transactional queries?
So analytics is something which is very difficult to have on the fly with transactional workloads because there's typically this phase of synchronization between the transactional workload and the graph that we are running analytics on, and they are never usually up to date. So analytics is usually run on a copy of the graph, which we expect it to be a bit in the past, and we are still okay with it. As far as transactional workloads on graphs, it can be utilized as such, but performing analytics over a graph also doesn't involve any writes. So there we actually don't need synchronization. So it's two different problems. It's the step that that's the delay between the transactional update to when it's reflected in the analytical workload is where complexities happen.
So if you had one more year to work on this thesis, how would you like to extend it? Like what would
Okay.
be the?
So the first thing that I want to achieve, if I had one more year, is to first get it into MongoDB.
Okay.
And that I find is one thing which would really motivate the use of CLog, because it's a very elegant solution in my opinion. And if implemented in a database like MongoDB, which works on JSON, it would really show performance improvements. And if I still had time beyond implementing MongoDB, I would then like to go back to the Tinkerpop implementation that I have and do this workload analysis over the graph.
Thank you very much for your insightful answers. They demonstrate you're really an expert in the field.
Thank you.
Thanks. Okay, let's continue with advisors. Soit, if you want to start.
Il m'a passé une question, not a file to I just want to advise that it was a pleasure to work with you.
It was a pleasure for me as well.
Things are clear on the rest, nice. Thank you for your work on the good presentation.
Thank you.
Julien?
You can ask questions if you want.
No, I have no questions today. So, first I switch in French pour souligner le fait que, en plus de tout ce que tu as présenté pendant ces 3 années, tu as appris le français. Et il y a beaucoup de doctorants qui sont passés dans l'équipe et qui sont pas sortis avec le français une langue difficile. Donc, bravo pour ce point-là. Je ne vois pas dans l'exposé.
Merci.
La deuxième chose, c'est quand tu es arrivé dans l'équipe, tu venais de plusieurs années d'ingénieur, tu es arrivé avec une très bonne réputation de technicien. Et je trouve que le point le plus fort de ta thèse, c'est d'avoir su, et c'est pas toujours facile, switcher à quelque chose qui est plus scientifique, trouver un problème. Et le problème que tu présentes aujourd'hui, c'est toi qui l'as apporté. Ça, il faut le souligner. Et c'est vraiment un point fort. Tu as su convaincre tes encadrants que c'était vers là qu'il fallait aller. Et enfin, le troisième point, c'est que j'attache énormément d'importance à la partie expérimentale, étudier chaque petit point. Et ça a été un plaisir de travailler avec toi parce que c'était ultra rigoureux. Et tu as vraiment cette approche au système en toi. Bravo. And now I switch in English for your family. And
I hope they're watching.
You can be proud of you. First, because you are a very nice person. And second, because you have all to become a great scientific researcher. Perhaps not as a plant doctor. Evans, you talk a lot
Others
about
going to be disappointed.
grind to death, but as in computer science, for sure.
Thank you.
I know you are expected in India, but we are very happy to keep you in France for months.
Thank you. France has half of my heart.
So thank you for this.
Thank you.
And Mark.
Yeah, thank you. So I know Ayush for a long time. We worked during before his master's thesis and then during his master's thesis, which he did on the antidote database. And I always enjoyed working with you.
Thank you.
It was great. I completely agree with everything that Julien said, and I want to reinforce it. Another thing I like, I mean, it's also very enjoyable to work with you because you're very responsive and you know a lot and you're very sure of yourself, sometimes a little bit too sure, but you know, it's definitely a strength. I guess after 4 years or 5 years working together, I shouldn't have any more questions, but I do. So one of the questions is on this slide. So you say that CLOC should work better in complex hierarchies. Did you try that? Did you actually do
Yes.
benchmarks comparing, making the hierarchies more and more complex?
Yes.
And have you compared with other? So
Yes.
so do you have any slides with these benchmarks?
I don't have concrete slides with those benchmarks, but you can easily infer those results. So in any chart that talks about hierarchy sizes, it's not just the number of vertices and edges that increase, it's also the complexity of the hierarchy.
Mhm.
So a large hierarchy is more complex than a smaller hierarchy, which is where you really see this difference in performance. So for example, if you compare the tops of these bars on a small hierarchy versus a large hierarchy, you see a huge performance improvement.
I'm not sure that's really fair. I mean, you could have a very large tree, which is not a complex hierarchy, and according to your previous slide, CLOC would be worse than,
Yeah.
say, a dumb lock
Okay.
on a tree, or even intention lock.
Mhm.
Right. So that's my question. Have you tried going from a tree to something that is very bushy?
Yes.
And what is
I-
the results?
So, okay. Yeah, it's exactly what we had expected. With CLOC, it's actually not worse than DOM-lock and multi-interval DOM-lock. It basically gives the same performance as DOM-lock and multi-interval DOM-lock or FlexiGrand for that matter, with just a higher memory footprint. So if you compare these three for intention lock, DOM-lock, MID, everything, including CLOC for a tree, for example, you see the same performance because log grains in a tree are basically the lowest common ancestor, because there's unique paths, all of these techniques lead to the same vertex. So the log granularity is always the same. It's only the memory footprint of these different approaches that changes. So CLOC is more expensive in memory, but still gives the same throughput compared to others for a tree.
I'm still puzzled by something. You also said that a CLOC would not work for a graph database, and a graph database, the problem with the graph database is that it's too complex.
The
So-
problem with the graph database is not that it's too complex. The problem with the graph database is that we cannot restrict the number of roots we have.
It's too complex.
No. It's just that it has too many roots. If you can find a rooted, if you, for example, take a complete graph. A complete graph has edges between every pair of vertices. So it is a very complex graph. But if I identify a single vertex to start my labeling from, CLOC works exceptionally well for complete graphs.
Because it locks everything. It's
No.
the same as coursework.
No,
No.
because in a complete graph, the grain is dependent on the paths, and the higher the average degree, which is basically equals to V for a complete graph, the better CLOC's performance gets. So with graphs, it's the fact that we have multiple roots, which really leads our labeling to become more inefficient. That causes us to not get high performance.
So, I had another question, which is intuitively, the drawback of CLOC is the set.
Mhm.
And the complexity of, so the footprint and also the complexity of doing set comparisons. Did you actually measure that is the case, that's where the bottleneck is?
Yes. In any benchmark that has threads on, in any benchmark that has threads on on the x-axis, for a single thread, it's only the complexity of set intersections that causes this performance hit, because there is no concurrency, there is no conflicts, there is no concurrent locks. So it's only the metadata computation that is more expensive. So any of these charts show these results, and as you can see, the latency is pretty high compared to other MGL techniques.
Okay, I'm done. Thank you.
Thanks.
So I will ask you a few questions, but first I really want to thank you for the quality of your manuscript. I read it this weekend, and it was a real pleasure. So it's rare, and everything is extremely clear. Really, I want to thank you a lot. The presentation was also perfect, exactly as clear as the manuscript, so it's really impressive. I enjoyed your subject. It's funny. No, it's a good game. I would say it's difficult because you are targeting a problem that is known to be difficult, and you found really interesting ideas to optimize the way we lock nodes. So really a good work. I want to congratulate you. So again, two questions, because we are late and we all want to eat at some point. The first one is that you have another technique that is widely used when we have concurrent access on the data sets. This technique consists in using a kind of consistent snapshot, at least for the read. And I don't see how your work relates to this kind of approach. I mean, not so far from transactional memory or this kind of approaches.
So if I talk about snapshots, then concurrent isolated snapshots are actually, in my opinion, orthogonal to locking. I mean, if you can take efficient snapshots, then you really should not use locking because it's trying to solve the same problem using two different solutions. With snapshots, the problem that I ran into, so it's perfectly fine to take snapshots when your workload is read heavy, because you end up creating fewer snapshots and you don't get this thing that I call versioning tax, where every single time you create a snapshot, you now have to deal with, first of all, making sure that that snapshot is correct. Once that snapshot becomes obsolete, you have to garbage collect it as well. So it's all the additional mechanisms that are associated with the snapshot, which in connected data make them less viable, because when reading data in hierarchies or graphs for that matter, our snapshot sizes are not restricted in the way that they are for key value stores. So with key value store, I know exactly which keys I'm going to read. I create a version of them. But for example, for pattern matching on graphs, I don't know how vast my pattern match is going to be. So it's the creation of a snapshot for graphs is very expensive.
Okay, I better see this. So something that is very strange to me, and it's really because I never used graph-oriented database and this kind of data structures, at least with logs, is that at some point, when you want to take a log on some nodes, you have to find these nodes. So it means that you have to start from the root and you will have to traverse your graph. And I don't see, basically to do that, to find the nodes that you want to lock, you will have to take a big lock on the graph.
But it's a read lock. But it's a read lock. So multiple threads could be doing this traversals and finding which vertices they want to lock. And that's considering that we don't have an index. So if you have an index,
that we don't have an index.
So there's no optimizations that are specified, but you could as well traverse and search using a read lock. And it's not always the case that we start from the root. Very often we start from a data point that we already know where it is, and then we start our traversal from there. And that also leads us to have smaller grains.
Okay, I better see the use case.
So the case of always starting from the root was actually true when intention locks were designed, which is why they always start locking from the root. But in modern use cases, it's not really true anymore. We can start at arbitrary point positions in the hierarchy and perform traversals as we wish.
Yeah, it relates to another question. I don't see why you need a root, except for labeling.
It's only for
why
labeling.
not, if you have a random graph, why not choose just a random node? You say, okay, it's the root node, let's go.
Sure, but then you cannot ensure that every other vertex is reachable from this route. So any vertex that is not reachable from this randomly chosen route will not get a label. And because it doesn't get a label, it cannot be locked.
Okay. It's because you have a directed graph
Uh-huh.
and not, okay.
If it's an undirected graph, then we run into another problem, which is the direction of lock. Does my grain go from the leaf to the root, or does it go downwards?
Yeah.
And then we have to choose a direction arbitrarily, which then would add a third level of conflict, which is which direction is my grain now?
And I have a last question. You already asked many questions. Perfectly interesting. It's really a system question. When we see the results, so the CA lock really shine when we have a lot of threads. But when we have few threads, the results are not as good as we could expect. And in this case, using coarse grain lock or medium grain locked could be useful. Did you investigate how to switch from one locking scheme to another when you have different kind of workloads?
So I know how it can be done. I didn't actually implement it, but the problem with having this hybrid locking approach is to then, so you can acquire locks perfectly fine. You can relabel the hierarchy, perform structural modifications perfectly fine. It's only conflict detection where this complexity occurs. The grains that I define with, for example, DOM lock are different from the grains that I define in CA lock. And if I use these two techniques, instead of using these labels to identify the grain overlap, I now have to actually go and perform traversals in the hierarchy to find whether there might be a reachability check, because I have no way of comparing whether these two integers that I'm seeing in the log pool actually correspond to a grain in CA log.
Okay, you don't have any correspondence between DOM lock and the way you label the nodes. What you say?
Yes, and that's the problem that exists in FlexiGram. So what FlexiGram does is it creates fine-grained and it creates fine-grained lock and DOM lock on the same hierarchy. So at the root we have a fine-grained lock, and you can acquire it perfectly fine because we know that that grain is only the root vertex, and you can have concurrent DOM locks lower in the hierarchy. But its performance really takes a hit because now every single time I have a conflict, or whether when I want to detect a conflict between this fine grain and DOM lock, I need to perform a reachability query between A and G. And that's basically a search on the graph, and graph searches are expensive.
Okay,
Thank you.
thank you. We will know.
On a réservé une salle pour les jeunes.
You booked a room? Okay.
Yes.
So we have to move Satya with us. I don't know.
There's another meeting link.
Satya disconnected and he said, please call him when
Okay.
it's time.
I'll send him. I'll just call him and tell him to connect to the.
Yes.
It's,
I'm looking for PhD
you
students.
have to find funding.
I am. No, but anyway, you will come in the group, Miss Claire.
You will have to deal with me for at least a year now.
We really have to wait or?
First slide on the.
It's okay?
back. It's okay.
Okay, so,
Just
I do. So the jury congratulate you for your presentation, which, like the manuscript, was very clear, well structured, and pedagogical. So sorry, I will switch with the exactly what is written because it's too complex to switch from one to the other. So Ayush successfully put his work on the design and evaluation of log algorithms for hierarchical data structures into perspective. He clearly presented his contributions to the field along with his significant achievements, ranging from algorithm design to realistic implementations and extensive evaluation with convincing representative workloads. Beyond the presentation, the jury appreciated the Ayush insightful answers to the many challenging questions, which cover the wide spectrum from distributed algorithm aspects to database and system-related consideration. His answers established his high level of research maturity, deep understanding, and extensive knowledge of the field. For all these reasons, the jury unanimously recommends Ayush be awarded the PhD degree in computer science from Sorbonne University.
Thank you. Thank you very much.
Shake your hand.
Thank you very much. I'll start from the left.
Yeah, congratulations.
Thank you very much.
The one is daring,
Thank
so
you.
the first step.
And I miss you. Thank you. Yeah, I have a lot of things to say, but I won't take any more time before you go and have some food because it was tiring. First of all, for Mark, if you wouldn't have asked me to be a PhD student, I don't think I would have even thought of doing a PhD because it sounded very daunting and something that only super intelligent people do, which I absolutely didn't consider myself after working for 6 months on antidote DB. So thank you for asking me to be a PhD. Julia, the number of benchmarks that you made me execute was, I think it made my thesis really good, but it was really annoying while I was a PhD. But thank you for making me analyze every single aspect of my algorithm and making sure that it looks what it looks like now. And thank you, Swan, for making me theoretically rigorous in defining what the complexities are like, what algorithms should actually be written as specifications. So I thank you for that. And finally, for all of the jury members and my colleagues, especially Sadiq, Benoit, and Laurent, who is not here, because I did a lot of trauma dumping on them. Because I knew that they were all PhD students of mine. So yeah, that's all. And I hope you enjoy the food that I have here. Thank you. Thank you, everyone.
You don't have to read the PhD stuff.
I do.
Le serment en français. Le serment du PhD.
Le serment. It's on the.
I don't know. I don't have it.
You can Google it.
You can Google it. You have to read something. No, it's not mandatory. You can refuse if you want.
No, I think.
Because you will make everybody upset. But
I think it's too late to refuse now. Yeah, I've already read it.
Now read it out loud.
Yeah.
in French or in English, as you prefer.
I'll do it in English because.
I don't know. It's doing French.
Yeah.
French.
Okay. En présence de ma père, parvenu à l'issue de mon doctorat en sciences et technologies de l'information et de la communication, Et ayant aussi pratique de ma quête de savoir, l'exercice d'une recherche scientifique exigeante en cultivant la rigueur intellectuelle, la réflexivité éthique et dans le respect des principes de l'intégrité scientifique, je m'engage pour ce qui dépendra de moi dans la suite de ma carrière professionnelle, quel que soit le secteur ou le domaine d'activité, à maintenir une conduite intègre dans mon rapport de savoir, mes méthodes et mes résultats.
Bon.